Hello, very good evening to all of you. So today I am going to give a lecture on the shear force and bending moment diagram part 3. In two parts I have covered the basics of the SFD BMD, the derivation of the bending moment and shear force, to the derivative of the bending moment with respect to x will give the shear force, and partial derivative of the shear force with respect to x will give the rate of loading. So all that I covered in part 1 and 2, and in part 2 also I have explained about the some questions of drawing the loading diagram from the shear force or bending moment diagram and vice versa. So in part 3 I will cover the once again the drawing of bending moment and shear force diagram from the loading diagram and vice versa. And in addition to this I have covered some of the additional problems of competition levels of some higher level. So I hope you will enjoy my lecture. So let's start. First of all, loading and bending moment diagram. How to draw the loading and bending moment diagram from the shear force diagram, or loading and shear force diagram from the bending moment diagram. So there are some properties of the shear force diagram. Let's start with the shear force diagram. The shear force diagram consists of rectangular or a series of rectangles if the beam is loaded with point load. Like this is simply supported beam. The shear force of this will be like this. Reaction will be W by 2, and shear force will be like this. This is plus, this is minus. So in case of point load or concentrated load, my shear force will be consist of a rectangles or series of rectangles. The shear force diagram consists of inclined line in the portion on which the UDL is acting. Suppose my loading is like this. So in this case, this is W, this is L. So WL by 2 will be the reactions. So my shear force diagram will be like this. This is plus and this is minus. So in case of UDL, the shear force diagram will consist of inclined lines on the portion on which the UDL is acting. The shear force diagram consists of parabolic curve for the portion on which the triangular or trapezoidal load distribution is acting. Suppose my loading is like this. So in this case, suppose this is the intensity. So total load will be, here it will be, this is B, this is A. So RA, RB. So this RB into L is equal to W into L by 2 into 2L by 3. So it will be WL by 3 RB into O. So it will be and here RA will be equal to total load is WL by 2. This is minus WL by 3. So it will be WL by 6. So if I draw the shear force diagram, it will be like this. WL by 6 and WL by 3. So it will be like this. So it will be parabolic in this case. So if my loading is triangular or trapezoidal loading, it may be like this. Trapezoidal loading, in both the cases, it will be a parabola. And the shear force diagram will consist of cubic curve for the portion for which the parabolic load distribution is acting. Suppose my loading is parabolic, so like this. If my loading is, so this is my loading, it is parabolic. So in this case, my shear force will be of cubic curve on this parabolic lead. So it is a y is equal to kx square. So in this case, it will be a cubic parabola. So it will be cubic parabola. So this is for shear force. And for bending moment, the bending moment diagram consists of inclined line for the beam loaded with a point load. Suppose in the first case, there is a point load, so its bending moment diagram will be like this. So it will consist of inclined lines for the beam loaded with a point load. And if there is a UDL, so in this case my bending moment will be parabola. So this will be a parabolic curve. Bending moment diagram consists of cubic or third degree for the portion for which the load distribution is rectangular or trapezoidal. Suppose my loading is like this. So in this case, my parabola will be like this. So it will be a cubic parabola. It will be cubic or third degree parabola. The bending moment diagram will consist of fourth degree curve for the load distribution is parabolic. Suppose if my loading here is parabolic, it is parabolic like this. So it is a parabolic. So in this case, my bending moment diagram will consist of 4 degree curve. So it will be a 4 degree curve. So it will be a 4 degree curve. Let's start to understand the things by illustrating the numericals. So let's take the first numerical. The shear force diagram for a beam for the with overhang is shown in a figure. Determine the loading on the beam end, hence draw the bending moment diagram. So this is the shear force diagram. So this is my shear force diagram, and with this shear force diagram I have to draw its loading diagram as well as its bending moment diagram. So here this is a case of overhang. So on both the side there are overhang, means this is a beam. Here this end and this end they are simply supported, this one and this one, and these two are overhang portions. So I can, this is my loading diagram, and there will be two supports at this and this. and there will be overhang. These two things are overhangs. If you look here, my shear force is suddenly it drops to minus 2 kilonewton. It means it is possible when a vertical download load of 2 kilonewton acts at these points. When this 2 kilonewton load acts here at this point, then and only my shear force will be minus 2 kilonewton here. It means here there is a 2 kilonewton vertical load, and from here to here, for this portion, my shear force is constant. What does it mean? It simply means that there is no vertical load. That's why my shear force is constant. And at this point, there is a sudden jump in the shear force from minus 2 kilonewton to plus 4 kilonewton. It means there is a sudden jump from minus 2 to plus 4. What does it mean? It means since it is a sport, so there is a vertical upward load of some amounts. So if suppose this is minus 2, if I add something, suppose this is the reaction at B, if I add this, then it will become plus 4. If I add the reactions, that is a vertical upward loads, that is a RB, reaction at B, then it will become plus 4. So RB will be plus 4 plus 2. It will be plus 6 kilonewton, means it is upward. It means there is a vertical reactions of 6 kilonewton at B. Then if you see here, from here to here, my slope of the shear force is constant. The slope of the shear force means my derivative of dfx upon x gives the rate of loading. As my rate of loading increases, my shear force decreases. That's why it's minus. I explained in my early classes. So its slope of this shear force, since it is inclined, it means there is a UDL. In case of UDL, my shear force will consist of inclined lines, and its slope of the shear force will give the rate of loading. So suppose if I want to know its slope, then this is a triangle. If I meet, this is 4 kilonewton. If I meet with the horizontal line, then its slope, this is angle, so its slope will be equal to this side divided by this side. So it is equal to, otherwise I can say this is the line. Let's draw a horizontal line and draw a vertical line. So this is the triangle. So its slope means dy upon dx. Its slope is tangent theta is equal to dy upon dx. So this side upon this side will give its slope. So this is 4 plus 5, this is 5, this is 4. So this total is 9 kilonewton. So this is 9 and this is 6. So this 9 upon 6 will give the slope, and it is equal to 1.5. So it means my rate of loading is, its slope will give the rate of loading. So its slope is 1.5 kilonewton per meter. It means there is a UDL of 1.5 kilonewton from here to here, and since there is no load is acting here, so that's why there is a continuous slope. My slope is constant, so it means there is a UDL, and in addition to a UDL there is no any other load. So this is a UDL of 1.5 kilonewton per meter. Then again, if I see my shear force at this point is minus 5 kilonewton. So minus 5, then there is a sudden jump. So from right side it is plus 3. So in minus 5, what should I add so that its value will become plus 3? So if I add this RC, this is the upward load, vertical reactions RC, in this minus 5, then it will become plus 3. It means RC is equal to 3 plus 5 is equal to 8 kilonewton upward. So it means there is a upward reaction of 8 kilonewton here. Then from here to here, my shear force is constant. It means no load is acting in this portion. That's why it is a constant. In this portion, no load is there. But again at D, it again become equal to 0. So this is plus 3. Then it is 0 here, and that is possible only when suppose there is a K amount of load, so that it becomes 0. So K will be minus 3. It means there is a vertical load of 3 kilonewton vertical downward, due to which it becomes 0 here on the just right side. So from plus 3 to again it is 0, or I can say plus 3 denotes the vertical download if I start from the right side. So now this becomes my loading diagram. So this is my loading diagram. From this loading diagram, I have the value of both the reactions RC and RB and everything which is required to draw the bending moment diagram, that's available on the screen. So with this I can draw the bending moment diagram. So this is now very easy. Once I get the loading diagram, I can draw its bending moment diagram very easily. So let's start from A. So my bending moment is MA is equal to 0 here. Since at this point my bending moment will be 0, and at B it will be hogging. This will act like this, so it will be hogging 2 into 2. So it will be minus 4 kilonewton meter. So this is, and it will be a linear. In case of vertical concentrated load, my bending moment is inclined line, it's linear. And if I start from here, then at bending moment MD and MA both are equal to 0. It is 0 here, and here at MC it will be 2 into this distance, 3 into 3, and it is hogging. Hogging means sagging is positive and hogging is negative. This is the sign which I have taken. Some of the books follows the different sign conventions. This is what I follows, and you can follow this. So this will become 3 into 3 minus 9 kilonewton meter, and this is also due to vertical load, so it will be a inclined line. This is straight line. Then my shear force will be maximum where my bending moment will be maximum where shear force is 0. Where the shear force changes its sign from positive to negative, or I can say shear force is 0, that point will give the maximum bending moment. So my shear force is 0 here, it is changing its sign. So this is the locations at which bending moment is maximum. So for finding this location, I can easily find from this shear force diagram. Suppose if this is x, suppose this is x from here, this is x, and this will become 6 minus x. So both the triangle are similar triangle. So this 4 upon x is equal to 5 upon this side. With this I can get the value of x, and that will be equal to 2.66 meter. As I solve this, will be 24 minus 4x is equal to 5x. It will be 9x is equal to 24. So x will be 24 upon 9 means 8 by 3. So it will be 2.66 meter. So this is the location where my bending moment will be maximum. So for finding the bending moment, maximum bending moment, I will, so this location is 2.66 meter from here where my bending moment is maximum. So bending moment maximum will be mx will be equal to here. So at this point I have to take the bending moment. So it will be this 2, it will be hogging 2 into this much distance, which will be equal to this 2 plus this 2 plus 2.667, and this will create sagging moment plus 6 into this much distance, and again due to this UDL it will be hogging again. So it will be minus intensity is 1.5 into this distance is 2.66 square by 2. So that value will give the this one. So it will be equal to 1.33 positive means sagging. So this value will be 1.33 kilonewton meter. This is maximum here. So this is the position where bending moment is maximum. This I know, and there is a UDL in between. It means my parabolic equation, my parabola will be like this for this bending moment. So my bending moment equation will be parabolic in nature. So it will be like this. Now this is my bending moment diagram. So let's come to the next questions. The bending moment diagram of a beam AB hinged at A and D. So there is a beam. So this bending moment diagram is given. This one is given. So what he says there is a beam AD hinged at A and D. So it means this is a simply beam. It's and A and D both are hinged means simply supported, and is shown in figure. Determine the loading on the beam and draw the shear force diagram. So for For drawing this is the bending moment diagram is given, and this is the beam A and D, both are simply supported. This one and this one both are hinged. So from this bending diagram, I have to draw the loading diagram and its shear force diagram. So let's start. So if I see, then my bending moment at this point is 0. MA is 0. So obviously there is a vertical support. So this will be, so this bending moment at the hinged end is 0, and at this also my bending moment is 0, MD. And at this point B, which is 5 meters from here, from this A, my bending moment is plus 10.625 kilonewton. Okay. So it means if I write equations of bending moment at MB, so MB will be equal to this RA I don't know, into 5, this will be second, and there is a load intensity which I don't know, suppose it is W, minus W into, since it is parabolic, it means UDL is acting here from here to here, so it will be W into this 5 square by 2. So that bending moment will be equal to this one, plus 10.625. So this is one equation. Another equation is the bending moment at this end, bending moment is plus 11.875. So another equations, MD, this is MC, sorry, will be equal to RA into this much distance, which will be 5 plus 2.5 means 7.5, minus this is W into 5, and it will act at a half of this. So 5, it will be 2.5 and 5. So it will be 5. And since my bending moment, this is a straight line. Straight line means its slope is constant. So the dmx upon dx, slope of the bending moment, will give your shear force Fx. So this will give shear force. So this is my bending diagram. So its slope will, since its slope is constant, it means my shear force will be constant. So that shear force will be constant means there is no change in the, this is constant, means shear force is constant, means no load is acting in this portion. So simply RA into 7.5 minus W into 5, it will act at this one. So the value will be, this will be minus plus 11.875. So this is one equations in forms of RA. So RA here will be, it will be RA minus 5, it will be 2.5, W is equal to plus 10.625 divided by 5, and here RA will be RA minus this will become 25 upon 7.5 W is equal to plus 11.875 divided by 7.5. So now I have two equations in form of RA and W. So with the two equations I can find the value of RA and this W. So from these two equations the value of RA and RB will be 3.75 kilonewton. If I solve this, it will be so 3.75 kilonewton and this is 0.65 kilonewton per meter. So these are the two values which I will get from these two equations. So after solving these equations, there are two variables RA and W. So with this, I can calculate reactions RA and W. So now it means my reactions RA is equal to 3.75 kilonewton. This load intensity is 0.65 kilonewton per meter. So these two values I have received from these two equations. So these are the values. Now so if I draw the shear force diagram parallelly, suppose, so it will be like this. This is my baseline. So this reaction will go 3.75 upward. Then due to UDL, it will be my shear force at this will be 3.75 minus 0.65 into this much distance into 5. So it will be 3.75 minus so it will be plus 0.5 kilonewton shear force. So if I draw the shear force, it will be plus 0.5 kilonewton here. And as I know, no vertical load is acting. Since shear force, its slope will give the shear force and shear force is constant. So shear force constant means for this portion means this 0.5 kilonewton will be constant from here to here. So it will be 0.5 kilonewton here also. And so parallelly my loading diagram will be like this. This is 0.65 kilonewton. These reactions I got. So at this C point, at this point, after I get this RA and W, I can find the bending moment here. So it will be this one. But if I see here at C, there is a sudden change in the bending moment diagram. Sudden changing in the bending moment diagram. So these are two supports, this A and this are hinged, and there is a sudden jump, there is a sudden decrease in the bending moment diagram at this C point. How is it possible? How is it possible? That is possible only when there is a movement, there is a couple. So if I see here, my bending moment at C just on the left, it is plus 11.875 and on the right side it is minus 0.625. Means if I add anything in this, Suppose if suppose I add m is the moment, then I will get minus 0.625. So that what will be the value of this m? It will be minus 0.625 minus 11.875. So it will be 12.5 kilonewton meter. So this value is minus. So minus means hogging. So there is a yes. So if I see this m will be, I had something in this, so m will be equal to, so there is a 11.875, this is positive, and if I add anything here, it will be minus 0.625. So m will be minus 625 minus 11.75. So it will be minus 12.5 kilonewton. So minus means, if I see from here, then it will be like this. So this will be, from this side it will be hogging. So as if I am starting from here, my this moment clockwise is positive and anti-clockwise is negative. So this is anti-clockwise, means on this side it will like this. So there is a hogging movement. So this will be anti-clockwise. So there is a couple of 12.5 kilonewton minus. So this couple is acting here 12.5 kilonewton. So I will place a couple here 12.5 kilonewton meter, and so this is the moment here. So MC is equal to minus 12.5. So this is a hinged hand. So I can find the reaction here. So this will be equal to, after getting this moment here, it is minus 12.5 kilonewton. If I start taking moment at this from here, it will be RD. Suppose this is RD. Initially I assumed like this, RD into this much distance, this is 2.5 equal to minus 12.5. So RD will be RD into this distance is 20.5, and it will be equal to 2.5. So it is 2.5, and this is 12.5 kilonewton. So RD will be 12.5 upon 2.5. Oh, this I think this is a vertical load. This is RC. RC is equal to minus RC into 2.5. Oh, yes. So there is a twist here. So just on the right side, my moment will be different. So my moment will be different on this side. So it will be, if I see my moment here, on the right side it is 0.625. It is not this. This is on the left side. On the left side it is this. On the right side it is minus point. So if I take this is 0.625, so this is 0.625. So it will be 0.625 minus upon 2.5. It will be 0.25 kilonewton, and this will minus means it is downward. So there is a downward. The reaction is downward. So this reaction is downward here. And in this case, one thing is also there. Since if I draw bending shear force diagram from here, since it is downward, so from this side it will be a positive shear force. So 0.25, if I start from here, it will be 0.25, and on the left side it is 0.5, on the right side it is 0.25. It means there is a vertical load. So there is a vertical downward load, due to which this becomes 0.25 plus x is equal to 0.5. So x will be 0.25. So if I start from the right side, my downward load is shear force due to this will be positive. So it means there is a vertical concentrated load of 0.25 kilonewton here also. So now this is my shear force diagram, and this is the loading diagram. So this is complete now. Everything. So there is another example. Figure shows the bending moment diagram for a beam ABC supported at A and B. Draw the SF and loading diagram. So this is the beam. So its bending moment is given. Bending moment of a beam AB is given, and it is simply supported at A and B. It is simply supported at A and B. It means if I draw the loading diagram, so this is my simply supported beam. So is A and B are simply supported. This has been given in the questions, and this is the loading diagram. I have to draw the SFD and the loading diagram. So this is a simply supported beam. Its A and B are, this is line diagram, A and B are simply supported, and I have to draw its shear force diagram and loading diagram. If I see here, at this simply supported end, there is a hogging bending moment of 60 kilonewton meter. So there is a hogging moment of 60 kilonewton meter. What does it mean? So I have to apply a couple here. So here initially there is a couple of hogging. Hogging means it will act like this way. So there is a 60 kilonewton meter is the couple here. So I will apply a couple of 60 kilonewton meter here. Then from here to here, the bending moment is a straight line. Bending moment is a straight line. So it means my bending moment is constant, and the slope of the bending moment will give the shear force. Will give the shear force. So this is 60 kilonewton meter, and so obviously at this simply supported beam there must be reactions of Ra that I don't know. If I start taking moment at this, it will be Ra into this much distance, which is 3 meter, and this is hogging minus 60, and this should be equal to, since my bending moment slope is constant, means my shear force is constant, and shear force constant means no load is acting here. So my shear force constant here is my, in between B and C there is no load, no UDL or no concentrated load. So there is no load here in between. So Ra into 3 minus this couple will give the bending moment here, it is plus 30. So Ra will be this 30 plus 60, 90 upon 3. This will be 30 kilonewton and it will be upwards. So this I get. So Ra and couple, and parallelly I will also draw the bending moment diagram. So now there is no load in between. Let's start his bending shear force diagram for this portion. It will be Ra, it will be 30 kilonewton, and there is no load. Since its bending moment is constant, means shear force is bending moment, slope of the bending moment, shear force is constant, means no vertical load. So this shear force will be constant from here, so it will be 30 here also. And again, if I start from this end and I know the bending moment here is plus 30, so there must be some reactions of Rb. So moment, if after taking moment from this side, it will be Rb into this distance is 3, this will be sagging minus. So there is a parabolic curve, it means this some UDL is acting here. So it will be, suppose it is W, so the W into 3 square by 2, and moment here will be equal to plus 30. So here I have two unknown, Rb and W. Okay. So this is a parabolic equation. So suppose if I take moment at MB, if I take moment at MB, it is 0. Bending moment at MB is equal to 0. From this side, it will be Ra, this is 30 into this much distance, it is 6. This is hogging minus 60, and no load is here. Then there is a UDL. So suppose it is W, this will also be hogging. So W into this 3 square by 2, this will give the bending moment at B. So this is equal to 0. From this equation I can find the W, load intensity. So this will be equal to 180 minus 60, it will be 120 into 2 divided by 9. So it will be so 80 upon 3. No, no. This will be 30 into 6 minus 60. So yes, since one thing is also there, this is not true. If I see from the bending moment diagram, my bending moment is maximum here. At this point it is maximum. So it means my bending moment maximum means my shear force will be 0 here. My shear force will be 0 here. So shear force at this point is plus 30 kilonewton. This is plus 30 kilonewton. On the just left side it is plus 30 kilonewton. This is my shear force. So at this point, just on the right side, my shear force should be 0. Then and only I can get the maximum bending moment. So my bending moment is maximum here, means my shear force is either it will change its sign or otherwise it is 0. If I put my Fx shear force here is 0, then my shear force can be 0. It can be 0 only when there is a vertical download of 30 kilonewton here. So I have to, then and only it will become equal to 0 here. So I have to apply a vertical load of 30 kilonewton so that it will become 0. Otherwise this moment cannot be maximum here. So to get the bending moment maximum here, I have to apply the same amount of 30 kilonewton so that my shear force become 0. It means there is a vertical load of 30 kilonewton. Now I can find my intensity. So now taking moment at B, it will be equal to 30 into 6. This is positive and this is minus hogging, and this will again be minus 30 into this much distance. This is 3 minus W, I don't know, into 3 square by 2. It will give the bending moment at B, which is equal to 0. So from this equation I can find the value of the W. So it will be 180 minus 60, 120 minus 90, 30. So it will be 30 into 2 upon 3 into 3. So this will be 20 upon 3 means 6.667 kilonewton per meter. So this will be my load intensity. 6.667 is the load intensity. Now I can find my reaction here. So this RB I can find. So as I know, total vertical load sigma V is equal to 0, means vertical total it is 30 plus this is 6.667 into 3. This should be equal to this RA plus RB. So RA is 30 plus RB. So this 30 and 30 will cancel each other, and RB will be equal to 6.667 into 3, which is 20 kilonewton. So there is a vertical reaction of vertical upward. This is 20 kilonewton. So this what I get in the loading diagram. So my loading diagram is now complete. From this I can easily draw its shear force diagram, which I had drawn parallelly here also. So after this I have there. So this is 30, and then from here to here it is constant. Then again it will be 0, and again it will be 0 minus this 6.667 into 3 is equal to minus 20 kilonewton here. Then it will be here. So this is my shear force diagram. This is positive, this is negative. So let's start the new numericals. Draw SF and BMD for the members of ABC and DEF. So this is the question. I have to draw its SFD and BMD. Let's start. So this is a vertical link. Suppose a bar. This has been connected. So both the part of the beam, this beam AC and this DE has been connected by some kind of link, vertical link or bar or rod you can say. So I have to draw its SFD and BMD. For that I have to draw its, first of all I have to draw its free body diagram. So free body diagram will be like this. Since these two ends are hinged here, so both C and D are hinged. So for finding the reaction here, I will take moment here. So it will be RF into, this is 4 minus 8 into 3 is equal to 0. This is hinged. So RF is equal to 8 into 3 by 4 means 6 kilonewton. So this is 6 kilonewton, this reaction. So this is 6 kilonewton. And RA also I can find from here by taking moment at C. So another RB is also required. So let's start from here. So this is 6 kilonewton. Suppose if I want to draw the free body diagram of this DF portion, it will be like this. If I cut it from here, then since this is 6 kilonewton, this is 8 kilonewton. It means my reaction here, that should be equal to 2, this RD plus this 6 should be equal to this 8. So RD it means 2 kilonewton. So this is 2 kilonewton. So now this is a free body diagram of DF portion. So for this load, since this load is vertically upward, so this must be vertically downward of 2 kilonewton. No moment, both is hinged, and no horizontal load since this is a roller. So if it is vertical downward 2 kilonewton, again for this rod it will be upward for the equilibrium, and in addition to the no horizontal arm moment is there. So this is the free body diagram of this rod. So it is vertically upward, then vertically downward of 2 ton. So this will be the free body diagram of this portion. So there is a vertical downward load of 2 ton here. Now if I take moments at A, it will be equal to, suppose this reaction is RB, so it will be RB, it is sagging RB into this 4 is equal to, these are hogging, so 2 into this 5 plus this 4 which is acting on 5 meter, 5 square by 2. So from this I can get the value of RB. So RB will be equal to, so this will be equal to 10 plus this 25 into 2, 50. So this will be 60 divided by 4. So this will be 15 kilonewton, 15 ton. So this will be 15 ton. So this is 15 ton reactions here. So this is 15 ton RB, and RA I can find because for sigma V is equal to 0 total. So this RA plus this is 15. These are vertical upward. So this should be equal to the total load. This is 2 plus this is 4 ton per meter into 5. So this will be equal to 4 into 5, 20 plus 22 minus 15, it will be 7. So 7 ton Newton, it is the reaction here. So my free body diagram is complete now. So from this I can easily draw its SFD and BMD. So let's start how. So here my bending moment is 0 for this portion. Suppose for this portion my bending moment diagram will be like this. If I see, if I standing here, then it will be moment at this is 0, and at this D point it is also equal to 0, it is also hinged. So it is just like a simply supported beam having a constant total load at this point. So this is 2 ton and this is 6 ton. So at this point bending moment will be 6 into 1. So it will be like this, 6 ton meter, and this will be sagging. From here also it is 6. So this is the bending moment diagram for this portion. And since there is no bending, only axial load is there, so here no bending moment diagram will be there for this portion. And for this portion ABC, it will be very easy. I can draw it. So it will be, if I see my movement at B from here, it will be MB will be equal to, this is 2 into 1, this is hogging, and minus 4 into 1 square by 2. So it will be minus 2 minus 2, minus 4 ton meter. So this will be like this. Due to parabola, it will be parabolic 4 ton meter. And it will be, so there will be some moment, maximum moment will be here somewhere where shear force will be 0. So if I draw its shear force diagram, it will be 7 ton, then 7 minus 4 into 4, 16, 7 minus 16 is equal to 9. Oh, sorry. So let's draw its shear force diagram here. Its shear force diagram will be, this is 7 ton baseline, so 7 ton, then 7 minus, this is 4 into 4, 16, 7 minus 16 is equal to 9. So it will be 9 here, minus, and so this is 9 ton, then again a jump of 15, so it will be 6 ton, minus 6 minus, this will be 4 into 1, so this will be 4 minus, so it will be 2 ton, and then, so this will be my shear force diagram. If I want to know the bending moment positions, so this will be where shear force is 0. So this location I can find from this. Suppose this is x, so this will be 3 minus x. So 7 upon x is equal to, this is 9 upon 3 minus x. So it will be 21 minus 7x is equal to 9x. So 16x is equal to 21, and x is equal to 16, 21 upon 16. With this I can find this point x. And after knowing this point, I can know its maximum bending moment. Otherwise, I can fx, make the fx 7 minus 4 into x is equal to 7 minus 4 into x is equal to 0. So x is equal to 7 by 4 here. So otherwise, in this triangle, it will be 7. Oh, it's 4 here. So it will be 4 minus x. So It will be 28 plus 7x. So it will be 28. So either side, either from this triangle or from making fx is equal to 0, I can find this position. This will be equal to x will be equal to 7 by 4 meter. So at this point my bending moment is maximum here. So m maximum will be 7 into 7 by 4 minus intensity is 4 into 7 by 4 square divided by 2. With this I will get the maximum bending moment here. And this will be equal to 6.125 ton meter. So its bending moment will be like this. So it is by diagram it is here it is thing 2 into 1 minus 4 into 1 square by 2. So it is 4 at this point. It is parabolic like this 4 ton meter. So this is hogging, and at this point, which is 7.4 meter from this end axis, my bending moment is maximum, and here the value is 6.125 ton meter. This is the maximum bending moment second, and this will be parabolic. So if I draw a line like this, it will be my bending moment diagram for this portion. So this is the location of the maximum bending moment diagram. This is 7 by 4 x. So this is for DF portion, and this is for ABC portion. This is my bending moment diagram. Like this. So I can either by part, otherwise. So this is the portion where bending moment is maximum. So x is equal to 7 by 4 is equal to 1.75 meter. This one. So this is my bending moment diagram. If I want to draw its shear force diagram, then it will be I can also draw its shear force diagram. So this is for this portion, this is 6 ton. So let's start from the left side. For ABC, this is the baseline. This is 7 ton positive. Then here it is minus 9 ton. 7 minus 4 into 4 minus 9 ton I will get here. And due to UDL, my shear force will be like this. And then minus 9 plus this is upward plus 15. So it will be plus 16 ton. So this is the here. And again it will be 6 minus 4 into 1. So it will be 2 ton. So this will be my shear force. And since only axial force is here, so no shear force and bending moment diagram. For this portion, I can easily draw shear force. It will be like this. This 2 is upward for this portion. This is 2 ton. Then it will be constant here. Then again 8 ton minus. So 2 minus 8 will be minus 6 ton. So it will be 6 ton minus. Then it will be constant here. And then again minus 6 plus this 6. So it will be 0 here. So this is plus and this is minus. So this is my shear force diagram, and this is the bending moment diagram. This one. So let's start another numerical. Draw BM and SFD for the member ABCD shown in figure. So this is the members has been shown, and I have to draw its SFD and BMD. So if you see, it is like this. This end is fixed. So this is like this. is a kind of bracket. So there is a horizontal load of P kilonewton here. So I can draw its free body diagram. Let's start from here. For DE portion, this is D, this is E portion. So this horizontal, there is a horizontal load of P. So for the DE, for equilibrium, there must be a horizontal load of like this, which is equal to this for the equilibrium of this one. And in addition to this, this will also create a moment P into L by 2, and to resist this moment, so there must be a bending moment of like this of opposite nature. So this will be equal to PL by 2. So this is the free body diagram for DE portion. And for CD portion, for this CD portion, it will be for CD portion, since this is in this direction, so this will act here. So this is P, and there is a moment which is opposite to its nature. So it will be in these directions, and again it will be equal to PL by 2. This is C, and so if this is P, so it must be equal to P, and no moment because of the forces. So again there must be a moment of this one amount PL by 2 opposite to this nature. So this is the free body diagram of CD portion. And for this portion, for this CB portion, my free body diagram will be like this. So it is like P here, so it must be like in this direction P, and there is a moment of this, then again there must be a moment of like this PL by 2, and in addition to this, no reactions or moment is here, so obviously it will be this one. And at this end also, or this is C and this is B, since no other load is acting, so obviously it will be, if this is in this direction, this must be in this direction P, and my moment will be opposite to its nature PL by 2. So this is the free body diagram of this one. No, this is I think wrong. Since this force will create a moment here, so my moment here will be equal to, this is P into its this distance. If this is P here, so this perpendicular distance is L, so PL, this will be in these directions, and it is in the opposite direction. This is clockwise, this is anti-clockwise, so PL, and this will be PL by 2. So net effect will be PL by 2 in these directions. So PL by 2 in these directions means this must be means the net moment here will be in this direction PL by 2. So to counteract this, moment will be in these directions. So it will be this one. So it will be like this. So this will be PL by 2. Net moment is this PL by 2, and this is P. And this for this portion, again, since this is P in these directions, so for this portion it will be like this. So at B, if I draw the free body diagram of this one, it will be like this. So this is acting towards right, so P that will act towards left, P, and this is anti-clockwise, so it means this moment will be clockwise here of PL by 2. So in addition to this, no other force and moment. So obviously at this end there must be a horizontal force of P like this, and this will be opposite to this, no vertical directions. So this will be PL by 2. So this will be my free body diagram. PL by 2, this is like this, and this one. So after drawing the free body diagram, I can easily draw its SFD and BMD. So this is the free body diagram. So let's start from here, and let's start its shear force diagram first of all. So if I see, then for this portion, if I start drawing its shear force diagram, it will be like this. Since only axial force is there and no vertical shear force is there, so it will be just a straight line here. So this will be straight line here. This is see the shear force for this portion, for this inclined portions. So if I draw its shear force, since it is P, so if I resolve this one, then it will be, and this angle is 45 degree. Since this is L, this is L, so this is 45 degree, means this angle is 45 degree. This will also be 45 degree, and this will also be 45 degree, 45 degrees. So this P is acting here. So P sin 45 degrees is the P upon root 2. So this will act like this, and this, since this P is acting, so its component will be like this, P upon root 2. For drawing its shear force diagram, so I will draw perpendicular to this inclined line. So this force, this is the axial force, I will not take into consideration for drawing the SFD. So for shear force diagram, this is P upon root 2. So this will be P upon root 2, and in between no extra vertical load. So it will be like this. Then again it will be P upon root 2. So this is the shear force diagram for this portion, and for this portion also. For this portion, so I am drawing my shear force diagram bending band by standing here, inside here, this one, and this one, and this one. For CD portion, if I see this C and CD portion, this CD portion, this is the CD portion. Since there is no vertical upward load, only axial forces are there. So shear force will be a straight line like AB. Then for this portion, suppose if I draw by, I am here, then here, then here, so here. If I am standing here and I am drawing this shear force diagram of this, then it will be like this. This is my, so this is P and this is P. So if I suppose I am standing here and I want to draw its shear force diagram, so it will be like this. Since it is downward, so it will be negative. P, then it will be constant here, then again, so this will be P and P. So this will be the shear force diagram of this portion. Now this is the SFD, and for drawing its bending moment diagram, so let's start part by part. I am sitting here. I am standing here, and my movement is like this. So if I see from this side, so this is hogging in nature. So this will be hogging in nature. So that if I sitting here, then it will be sagging. So you can choose any of the directions, either from the outside or from the inside. If I am sitting here, then I am seeing this beam, then it will be hogging in nature, and in between no vertical load. So bending moment will be like this. This is for AB portion. This is hogging PL by 2, and this is PL by 2. So this is hogging, and I am drawing on the tensile side. So this is minus. Either way you can draw the bending moment diagram. So this is for AB portion, and for BC portion, if I see here, for this portion, I suppose I am standing here and I am seeing this BC, means here. So this is hogging in nature again, and it is sagging here. So this is hogging here, this is sagging here. I am watching this beam from sitting here and seeing this. This is hogging here. It means PL by 2. Again, it will be minus, and here it is sagging PL by 2. So it will be here. So this will be the bending moment diagram. PL by 2 minus, and this is plus. For this portion, for CD portion, again no vertical load. So if I am standing here, then it is sagging here, and it is yes, it is sagging both sides. So it is sagging here, means it is positive, and I am drawing on this side. So it will be same. It will be PL by 2 and PL by 2. So it is like this, sagging. Then for this portion, my bending moment will be, suppose if I am watching from this side and seeing this beam, so it will be sagging here. It is sagging here, and it is 0 at this point. So bending moment will be PL by 2 here, and again it is 0 at this point. So this is sagging. So this is the bending moment diagram. So I have drawn the bending moment shear force diagram. This is my position. I am watching this one from this side, and this side, and this side, up from the outside. If I can draw also the diagram SFD and BMD by sitting here in this side, that will be the same only. So that doesn't make the difference. Now come to the next question. So there is a bracket, and I have to draw its bending moment diagram. So this is A, B, C, D and E, and there is a horizontal load here. So let's start his free body diagram. This free body diagram, starting from here, it will be like this. For DE portion, EF, this is EF. EF portion, this is E, and this is F, this is E. So this horizontal load is acting towards right side. Obviously, at this end also, my load will be like this, 10 kilonewton. And since this is also creating a couple of 10 into 0.5 means 0.5 kilonewton. So this is acting in these directions. To counteract this, there must be a resisting moment of 5 kilonewton meter. So this is the free body diagram of FE, and this is what I have shown here. For this portion, for ED portion, it will be like this. This is acting towards left, so this will act towards right, 10 kilonewton. This is anti-clockwise, so this must be clockwise, 5 kilonewton meter, and no vertical load. Here also no vertical load. So again it will be 10 kilonewton here, so it will be 10 kilonewton. And this, since it is in these directions, so obviously this must be opposite, 5 kilonewton meter. So this is the free body diagram of this ED portion. This is E and D, this much ED portion. This I have shown here. For this DC portion, this acts towards left, so it will be towards right. This is anti-clockwise, so this must be clockwise, opposite to this. And again no vertical load, so there is no vertical or axial force here. So at this point C, if I know my total moment because of this will be hogging 10 into this 10 into this much distance into 1. This 10 into 1 will be in these directions, hogging, and this will be sagging. So it will be, suppose if this is minus 10 into 1 minus 10 kilonewton, this will be hogging, and this must be sagging. So it will be minus 5. So minus 5 will be hogging, and this must be in this direction. To resist this, so there must be a moment in this direction of 5 kilonewton meter. So this is the moment here, and again this is acting towards right, so this must be towards left of the same amounts. So this is the free body diagram of this DC portion. And for drawing the free body diagram of this AC portion, it will be like this. This is 10 kilonewton towards left, so it must be towards right of same amount, 10 kilonewton. And this is clockwise, so this must be anti-clockwise. So same, this is 10 kilonewton towards right, so it must be towards left. And since it is anti-clockwise, so this must be clockwise, opposite to this, and this will be equal to this is 5 kilonewton, I think. This is 5. This will be 5 kilonewton in these directions. So now my free body diagram is complete now. Let's raise this one. So now this is the free body diagram of all the members. Now easily I can draw its bending moment diagram. So here I am sitting here inside, this one, this one, this one, and this one. Or you can say, yes. So for this portion, for AC portion, this is the AC. So this is my AC baseline, and this is 5 kilonewton meter. This is also 5 kilonewton. If I see here from this side by standing here, so it will bend like this one. Means this is a sagging moment of 5 kilonewton. Sagging means positive. So I can draw either this side or this side. So it means sagging moment of 5 kilonewton. Suppose I am drawing on the tension side. So I can draw it like this. So this is the baseline, and this is 5 kilonewton. So this is 5 kilonewton meter. This is positive. And for this CD portion, this is a free body diagram. So if I am watching this from this side by standing here, my beam will deflect like this. So it will be sagging here, and this is a hogging here. So there is a hogging here. It will deflect like this. This is hogging. You draw the arrow. So arrow is acting in this direction. So this is sagging, and this is, you just see the arrow when it hits the member. So it is sagging, it is hogging. So I will draw in this side. So this will be my, so this is 5 kilonewton again, sagging, and this is hogging here. So this is also 5 kilonewton meter, 5 kilonewton meters. This is positive sagging, and this is negative hogging. Then again, suppose if I am standing here and watching this, the beam, so it will be, by standing here and seeing this beam, so it will become hogging. From this side it will be hogging. From this side it will be sagging, but from this side it will be hogging. Since I am drawing my bending moment diagram by standing here, 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 and inside only, so for this it will be hogging, and its amount is 5 kilonewton meter, and here also it is 5 kilonewton. It will be minus hogging 5 kilonewton meter here, and it is also here. If I draw the bending moment of this portion by standing here, then it will be hogging 5 kilonewton. So it is hogging 5 kilonewton. Then again here it is 0. So it is like this. So I had drawn my bending moment by standing inside. So this is the position of the bending moment diagram, and either way we can draw it. If I am drawing by here, standing here, then also I can draw it. So that will remain the same. Next question. Sorry for that. So this is my frame, and I have to draw its bending moment diagram. So this is like this. This is a roller end, means there will be a reaction which is perpendicular to these directions, and in the direction of the roller no force will act here. So it is free here. So only one reaction will be in these directions. Suppose this is RD. This is RD, and this is RA. So for finding the reactions, suppose if I am taking moment here, so there will be, suppose this is theta, This is a triangle, this is a 2, this is 1.5. Means if I multiplied it by 2 and 2, it will be 3, 4, and this will be 3. Again this will be 5. So sin theta will be 4 by 5, 4 by 5, and cos theta will be 3 by 5. So this theta, if this is theta, then this will be theta. So this component will be r sin theta, this will be r cos theta. Rd sin theta. Sin theta is equal to 4 by 5, so it will be 4 by 5 Rd, and it will be 3 by 5 Rd. Suppose I am taking moment about A, so this will be Rd, this Rd sin theta is equal to 4 by 5 Rd into this much distance, perpendicular distance, this is 1.5 and 1.5, so this is 3. And again this horizontal, this will create moment in this direction. So effect of this, if I draw this way, this will also be in the same directions. So this will be a 3.5 upon Rd into its distance. Here this will be the perpendicular distance for this force, and this will be 4 minus this 2. So this will be 2. And this will be opposite, 9 into this 4. So this will be minus 9 into 4 is equal to 0. So Rd means, Rd, if I take this comma, this will be 12 by 5 plus this will be 6 by 5 is equal to 9 into 4, 36. So Rd will be equal to 36. This will be 18 upon 5. This will be 5 upon 18. Means 4 by 5 Rd into 3 by 5 Rd into 2 is equal to 9 into 4, 36. It will be 12 upon 5 plus 6 upon 5. So 18 upon 5. Oh, this is 36. So it will be 2 into 5 is 10. So this will be 10 kilonewton. So if this is 10 kilonewton, then this is 4 by 5 of Rd. So 4 by 5 for 10 it will be equal to 8 kilonewton. And this will be 3 by 5 Rd means 3 by 5 of 10 is equal to 6 kilonewton. So these are my reactions now. Now I can easily draw its bending moment diagram. So this is the free body diagram of this one. Let's start the free body diagram of CD. It will be like this. For CD it will be like this. This is D, this is C. So this is 10 kilonewton. So this will be 10 kilonewton for CD portion. And there is no bending since it is passing actually through the centroidal axis. No bending moment will be because of this one for CD portion. And for BC portion, I can also draw its shear force diagram. It will be, this is 6 kilonewton, this is 8 kilonewton. So this must be, this is 8 kilonewton means This must be downward here. This is 10 kilo. Suppose this is C. So this is 10 kilonewton. It will act 10 kilonewton will act here in the opposite directions. So this is 10 kilonewton. 6 kilonewton means it will act like 6 kilonewton. And this RD is upward. So obviously it will be downward. 8 kilonewton. So this is 10. This RD is upward. So it will be downward. This direction 8 kilonewton, and this is towards left, so this must be towards right. So this is the free body diagram of CD. For BC portion, this is BC. So obviously, if I see for this BC portion, if this is 6 kilonewton, so it means it is 6 kilonewton here, and if it is downward, so it will be upward of 8 kilonewton. And since it is passing actually here, it means no moment either here or here. So there is no moment. So for BC portion, it will be like this. So again, it will be a 6 kilonewton here, and this is upward, so it will be downward. So this is a free body diagram of BC. For AB portion, this is A, this is B. Since this is downward, so it will be upward of 8 kilonewton. This is towards right, so this must be towards. Oh. Yes. So here, since this is 6 kilonewton, so it is 9 kilonewton here. Means at this it will be, it is 9, so it means it is 9 kilonewton, means it will be like this, 6 plus 3. I can say like this, and this force will act. So at this point, my net force will be in this direction 3. So this will be 9 minus 6. So 9 is acting here in this direction, and 6 is acting in these directions. So net force will be like 9 minus 3, 9 minus 6. It will be 3 kilonewton. So it must be opposite to this here, and this will be I can also draw its diagram from here. And once, yes, for sigma V is equal to 0, as we know, this is a vertical reaction of 8 kilonewton here upward, and no vertical load is acting. So if it is upward, it must be downward. So this is 8 kilonewton downward. And my total force for sigma V is equal to 0 and sigma H is equal to 0. For that, this is 6 kilonewton. So this, suppose this is HA, this plus, suppose this is acting in this direction. So this plus this 9 should be equal to this one. For sigma H is equal to 0. So HA will be equal to minus 3 kilonewton. Minus 3 means it is not in direction, it is in these directions. So I can draw its free body diagram. It will be like this. So this is 8 kilonewton, this is 3 kilonewton. So obviously it will be here from this side 3 kilonewton and this will be upward 8 kilonewton. If I see from this position for this BC portion, it must be downward 8 kilonewton and this will be opposite of this. So this will act here in this direction 3 kilonewton. So 3 kilonewton is acting here and there is an addition of 9 kilonewton here also. So the net effect will be 6 kilonewton in this directions. So this must be 6 kilonewton in this direction. 9 is acting in this direction and 3 is acting here. So it will be 6 like this. If this is downward, it will be upward. So this will be the free body diagram. So this is my free body diagram now. All the portions for CD portion and this BC portion and this AB portion. So I can easily draw its bending moment diagram. For this CD portion, since it is axial and no transverse load is there, so bending moment for this CD will be 0. Number 1. For this portion, bending moment here is 0 and it is sagging. Suppose if I am sitting here inside and I am watching this. So this is sagging, means 12 kilonewton sagging. So I will draw. So it will be like this. So sagging, the BC is 12 kilonewton and this is 0 here. So this is positive. If I am standing here and watching this one, so my bending moment here is 0 and this is here. So if I am watching, this is sagging. So this must be like this. So this is sagging. So this is 12 kilonewton and it is 12 kilonewton and so this is sagging. So this is my bending moment diagram. I can also draw its shear force diagram. So shear force diagram, once I know the directions. For this CD portion, only axial force is there, so its shear force will be 0 like this. And for this portion, this is downward. Downward means negative shear force 8 kilonewton, then no load in between, then again 8 kilonewton. So this is my negative shear force. For this portion, by sitting here, so this will be upward. So if I am watching from this side, so upward means positive shear force. Positive means so this is 3 kilonewton here and it will be constant here. Again, this will be in this direction. So this is my shear force diagram. So this is the complete solution now. So sorry for the disturbance. So this is the last question. A simply supported beam ABC, is loaded as shown in figure. Determine the location at which a concentrated load of 2.5 kilonewton. So this is my simply supported beam. What he wants to know, that I have to find the location at which a concentrated load of 2.5 kilonewton must act from A. There is a concentrated load of 2.5 kilonewton which is acting at a distance of A from this location. So the locations. To make the reactions at A and B equals. This is my loading diagram. So what he wants to know, that suppose there is a vertical load of 2.0 kilonewton. At what location I should place here, here. show that my two reactions at A and B are equal to each other. So that location I have to find first of all. For this location, draw the SFD and BMD. This is second task number 2. Third, locate the point of contraflexure. So there are three things: location of contraflexure, then drawing of SFD and BMD, and first is the location of this 2.5 kilonewton where I should place this, show that my vertical reaction at A and B are equal to each other. So this is my loaded diagram. Suppose the location where this load is acting, this is at a distance of A from this spot. Okay, so this is at a distance of A from here. Now, and in this condition, my reaction at RA and RB is equal to each other. Now, for sigma V is equal to 0, my total vertical load is equal to RA plus RB. They are acting upward. So this is RA, this is RB. RA plus RB is equal to vertical upward load should be equal to the vertically downward load. So this is equal to 2. This load due to this triangular loading is equal to area of this one is equal to 2 into this is also 2 divided by 2. This is the area of the triangle. So this is the load of this plus 2.5 kilonewton because of this concentrated load, and this is also 2 kilonewton. So total will be 4.5 plus 2, 6.5 kilonewton is the total vertical load which is acting downward. So this must be equal to RA plus RB. Now, my both the reactions are equal. What he says, it means RA is equal to RB. So it means this is 2 RA is equal to 6.5. Then RA is equal to 3.725 kilonewton, and RB is also equal to 3.25 kilonewton. So both are vertically upwards. So these are my reactions now, 3.25 and 3.25. So these are the vertical reactions of 3.25, 3.25 both here. Now I have to find these locations where this load is acting. So for this is the load, and I have to find out locations. So this is the distance here. A simply supported beam ABC is loaded as shown in figure. Determine the location at which these concentrated loads must be act from A so as to make the reactions A and B are equal to each other. So my reactions are 3.2 and 3.2. So both are equal. Okay. So suppose this is the distance. This distance is A from here. So this is 3.25 kilonewton, and this distance is A. This is also equal to 3.25 kilonewton. So it means total, these are the reactions, and if I start taking moment here, suppose if I am taking moment at this end, then from RB side it will be equal to taking moment at this point. It is 0, MA is equal to 0. So it will be equal to RB, which is 3.25 kilonewton, into this much distance, which is 4 meter, and this is positive, since it is sagging, minus this is hogging 2 into 5, it is hogging, and this will also be minus, it is 2.5 into this much distance, minus 2.5 into A, and this will also be minus because of this triangle load. So area of this triangle, it is 2 into 2 by 2, that will be the area, and this will act at 1 by 3rd of this month length. So this, if it is 2, so it will be 2 by 3rd where it act. So this should be equal to 0. From this equation I can find the value of A. So this is equal to, since this will be 13, so 13 minus 10 minus 2.5 A, this will be equal to 4 by 3. It means this is 3. So minus 3 minus, oh, this will be, no, this will be plus 3 minus 4.3 is equal to 2.5 A. So this will be 5 by 3, and this will be 5 by 2. So A will be 2 by 3. So 2 by 3 is equal to 0.667 meter. It means this distance A is 0.667 meter from this spot. So this A is this one, 0.667. So I have found the location of this concentrated load so as to make the reactions RA and RB is equal to. First I have find the RA and RB by from the condition of sigma V is equal to 0, then by sigma M is equal to 0 by taking moment here and putting the value of RB, I can find this I. So this A is equal to 0.667. So now I have the reactions 3.25 kilonewton, this one and this one, and this location is 0.667. This is 0.667 meter. So for these locations I have to draw the SFD and BMD. So this is task number 2. This is my baseline, and first I am drawing the shear force. So it will be equal to, let's start from the right hand side. For right hand side, if I start from the right side, my downward will be positive. So this will be positive shear force of 2 kilonewton. From here to here it will be constant. Then again this is 2 pulse, and this upward will become negative if I am starting. So it will be opposite to this. So this will be minus 1.25 kilonewton here. So this is 1.25 kilonewton is the shear force here. And since no load is acting here, it means it will be constant. It will be a straight line. It will be constant from here to here. From this is D end. And then from here to here, it will be, due to triangular loading, my shear force will be parabolic in nature. So if I want to know the shear force at this point, which is at a distance of x from this D, then Fx will be equal to, that will be equal to, this is plus 2, then it will be minus 3.25, because of this, and the area, this is downward, so downward means again it is positive, so it will be, I am starting from the right side, means downward is positive. So area of this triangle will be equal to, at the loading intensity it is 2, so this intensity Wx will be, this is 2 by 2, and if this is x, Wx, then it will be Wx upon x. So this will be Wx is equal to x. So this will become equal to x kilonewton meter. So this intensity is x kilonewton here. So this is x kilonewton meter. So shear force here will be the area. I will add this area. So this must be equal to, this is x, this is x. So x into x divided by 2. This is a triangle. So this will be the area here. So this is the shear force at this point. Fx is will be equal to, this will become minus 1.25 plus x square by 2. So here I can find the point where my shear force is 0. So shear force obviously, this is the x point. When x is equal to 0, my x is 0 here. My x is 0 here. So by putting x is equal to 0 in this equation, I will get my shear force at this point. So this is constant. It is minus 1.25 as I drawn earlier. This will be FD right side. And from here to here, this is a parabola. So this is parabolic in nature. So my shear force will vary parabolically. If I want to know the shear force at this E point, this is, since it is 0.667, this is 2. So obviously this will be 1.333 meter. Total is 2 minus this 0.667, it will be 1.33. If I want to know the shear force here, then I will put the value of this, x is varying from this side. So I will put the x value of x here in this equation. I will get the shear force at E, and that will be on the right side. So Fe right will be, this will be minus 1.25 plus x is equal to 1.333 square by 2. I will get my shear force, and this is equal to minus 0.361 kilonewton. And just on the right side, there is a variation due to this concentrated load. So this is acting downward, means it is positive. So I will add this value minus 361 plus this 2.5. So I will get 2.139. This one. This is 2.139 kilonewton. Then again, if I want to know the shear force here, then this I am already aware of this. This is 3.25 kilonewton. And this will vary like this, parabolic. So this is my shear force diagram. This is positive and this is negative. So this is SFD now. So for drawing the bending moment diagram, first of all, I want to know the position where my bending moment will be maximum. So this is the point. This is the point where shear force is changing its sign from plus to minus. Obviously, my sagging moment will be here. Since shear force is changing its sign, either it is 0 or changing its sign. So if I want to know the bending moment at this point, then it will be equal to, this is a reaction 3.25. So bending moment at this point, E point, will be 3.25 into this distance, which is 0.667, and this will be plus minus bending moment because of this trapezoidal. I can divide it into two parts. One is triangle and other is trapezoidal. So intensity here will be equal to, this x is equal to 1.337 3 meter. It is 0.667 here. So my bending moment at this point will be 3.2 into this one minus triangle, this triangle. Obviously this intensity will be 1.3333. Since x is equal to 1.3, so this intensity will be this. So this will be equal to 2 minus 1.3333. So 2 minus 1.333 means 0.667. So this is point. This will be 0.667. 0.667 into, this is 0.667 also, divided by 2. That will be the area of this triangle, and it will act at a distance of, this will be 2 by 3 of this one into 2 by 3 of 0.667. So this will be hogging, and again because of this triangle, this will also be hogging. This is equal to, obviously this is equal to 1.333 into, this is rectangle, into 0.667, and this will act at half of this one. With this I will calculate the bending moment here. So this will be equal to 1.772. I can also find the bending moment this from this side also. That will be, I think, easy. If I want to know the bending moment from this side, then it will be equal to M. This is E. ME is equal to, from this side it will be equal to, then it will be hogging minus 2 into, this distance is, this is 3 plus this, so it will be 4.333. This will be hogging, because of this will be sagging, plus 3.25 into this distance will be 2 into this, so this will be 3.333, and this will be again minus, this is 1.33 into, this is also 1.33, divided by this will be the area of the triangle, and this will act at 1 by 3 of this. So either way I can find the bending moment at this. This will be 1.772 kilonewton, and that will be maximum since my shear force is changing its sign. So, and here the bending moment here, so bending moment here is because 2 into this one, so it will be straight line due to point loss. It is 2 kilonewton here, so this is 2 kilonewton here, and at this point it will be 2 into this 3 plus 3.25 into this 2 distance, so it will be minus 6 plus 6.5, so it will be 0.5 sagging. So at this point it will be 5, and this will be straight line because no load is acting. So from here to here it is straight line. It is 0.5 here at this T point, and it is 0 here, and it is maximum at this E point where the shear force is changing, and this will be a cubic parabola. So this will be my shear force diagram. So this is the shear force diagram. Third question, third thing which he wants to know is the location of the point of contraflexure. Location of the point of contraflexure. point of contraflexion means where my bending moment is 0. My bending moment is 0, I am changing its sign. This is the location of this one. So if I see here, then this location is obviously somewhere here in this point where this changing its sign. So this is the point here. This is in this dB portion. So if I want to know my bending moment from this, suppose this is x, then bending moment at mx will be equal to so bending moment at this point will be 2 into this will be 1 plus x. This is 1, this is x, and this is hogging, so it will be minus. Plus because of this 3.25 into x, this will be sagging, and this bending moment at mx, this must be 0 for this location. So this is equal to 0. It means it is minus 2 minus 2x plus 3.25 x is equal to 0, means minus 2, this will be plus 1.25x. So it will be 2, this is equal to 1.25x, x is equal to 2 upon 1.25. So this must be equal to 8 by 5. So 8 by 5 is 1.6 meter. So this is 1.6 meter from this spot. From this B, it is 1.6 meter. This is the point of a contraflexure. So this is the location of contraflexure. My bending moment is maximum here. This A is this one, and these are my reactions. So the question is all. These are the calculations which you can follow. So that's it from my side. I hope you enjoyed today's lectures, and that will clear your concept about the competition level. So thank you very much and good night. Thanks.